Thank you for joining us today. Today we will be discussing dust collection system design for welding. This is just one of the many educational webinars we have for engineers. My name is Ashley Zook, and I am the channel manager here at Donaldson Company, working with engineering firms across the United States. One of the ways I help is through webinars like this and also scheduling in-person web or lunch and learns. Today we'll be reviewing the dust collector system design for welding operations, including ambient and source capture. Then we will review the 4 primary components for system design: the hoods, the ducts, the collectors, and the fans. And then we will finish up with a Q&A session. Just a heads up, it does take years of education experience to become an expert in dust collector system design. The goal of the session is just to give you a brief overview of the basics of welding operations. In case anyone here isn't familiar with Donaldson Company, we have been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the first filter for a tractor engine. Today, we are one of the largest providers of unique filtration technologies, and we excel at producing high-quality filters and parts. As you think of questions, please submit your questions in the chat box, and Jim will answer them at the end of the webinar. If you need to jump off early, don't worry. I will reach out to make sure your questions are answered. During the webinar, Jim will ask you a couple questions where you need to put up a thumbs up or a thumbs down. You can access these by clicking on the little face icon at the bottom of the screen. And with that, I am pleased to introduce our featured speaker today, Jim Hendrick. He has been working with Donaldson Company with the industrial air filtration for the last 28 years. He currently covers Oklahoma, Arkansas, and the southwest corner of Missouri. Prior to that, he spent 14 years working as a weld equipment manufacturer, including 9 years as a certified welding inspector. He earned his undergrad degree at Auburn University and his MBA at Oklahoma City University. And with that, Jim, I'll pass it over to you.
And thank you very much, Ashley, and welcome everyone. We've got a jam-packed hour here, and we're going to try to keep everybody on time. And of course, there is interaction with each one of you as we move forward. And we want to start out with asking a question. As you can see on the screen, we've got a choice A, B, C, D, E, and we're trying to get a level of experience. So if you would at this time, click what level you would rate yourself with the understanding of an experience of designing systems for welding.
All right, Jim, it looks like we have a lot of A's, a couple C's, some B's. We got one person that's got an E, so we got some experience in here, but we got a wide range of people.
Very good, very good. Well, that's good to know. It's important that we have a good understanding of who we're dealing with, what we're dealing with, and the information that we're going to convey. So hopefully this will be good for everyone. So button your chin straps and we'll get going. So first of all, let's just look at welding overview. There's many processes in the welding world, and we're going to be dealing with anywhere from manual welding all the way up to full automation, hard automation, and robotic welding. Each one, of course, each process, each type has its own way and has to be dealt with in a certain way in your engineered design of an industrial ventilation system. A lot of you may be familiar with these. If you're not, we'll just do a quick review. Gas tungsten arc welding, commonly known as TIG, shielded metal arc welding, stick electrode welding. You get into gas metal arc, which is very common. Flux core arc welding, it can be a self-shielded or a gas shielded type welding, and then submerged arc welding, which is a granular flux over top. So all of these different welding processes generate a weld fume, and that's what we're trying to do is design a system that will do the job properly. So what is in a weld fume? Of course, when you look at the chart here, there's many metals, many gases. You can pick one: chromium, hexavalent chromium. Most of you may have heard of that. The shielding gases, a lot of the welding processes require an inert shielding so that the molten pool of weld is not exposed to atmosphere, thus causing porosity. So this is what we're seeing in a weld fume. But what a lot of people for many, many, many years, they say, we'll just open the windows, open the doors, we'll let this blow on out, no big deal. Some companies are very proactive in this, others are not. But if you look at any box of welding rod or welding wire, you're going to see a caution sign. And of course, there's two of the caution signs right there. Welding fumes may be present. Yes, that's correct. Also, caution, welding may produce fumes and gases hazardous to health. Avoid breathing these fumes and gases. Use adequate ventilation. So therein lies what we're all about here. We're not the ones generating the weld fume, but we're the ones that are going to take care of the weld fume. One area that we could spend a day on would be, is the dust that we're dealing with considered combustible? Combustible falls into one of two categories, flammable or explosive or both. Real quick, you see at the bottom left here is what is commonly known as the combustion triangle. We have oxygen, combustible dust, and an ignition source. If you look far right here, what we deal with more and more is a flash fire and explosion, where we take the same combustion triangle, we introduce the combustible dust in a dispersible form under a negative, and thus an event. So you'll hear me reference NFPA a few times, and there are standards that are out there. The main thing that we want to take away from here is we must understand who the process owner is. You're going to get a call from a client. The client is going to tell you, you're the expert, you tell me. But we have to talk on the record. They are the process owner. They are the ones that are supposed to have a risk mitigation strategy. They are the ones that are supposed to talk with their authority having jurisdiction. That can be an insurance underwriter, a local fire marshal, or even a third-party consultant. But they are supposed to give you and I their risk mitigation strategy and how they want to deal with it. Unfortunately, that's not always the case. They still will push back to us. So we have to form it in a way when we present to them, this is our understanding of your application. We deem this to be conformant to NFPA, but they, the process owner, must deem it to be compliant with their risk mitigation strategy. So in that 30 seconds, hopefully I've opened your eyes that there can be combustible issues, whether it be flammable, explosive, or even both. So the importance of weld fume. First and foremost, safety concerns. There's hazards involved. We of course want to improve the quality in our facilities, and then your exposure levels. Depending on what you're welding on, there are certain thresholds that we must adhere to. Environmental concerns. Most people, weld fume, we'll just open the doors, windows, let it go outside. Well, EPA has standards for outdoor exhausted environmental air as well. And then the overall cleanliness of our facility. So we're going to address two areas that we can design for in weld fume. The first being source capture, and that's pretty self-explanatory. We're going to try to capture the weld fume at the source. When we capture at the source, typically that takes it away from the breathing zone. The two best filters in a plant is the lungs of the individual. So if we can attract this weld fume away from that breathing zone and then capture, filter, and exhaust either the atmosphere, a clean air, or back into the plant, we have done a good job. In most situations, the first choice is going to be source capture, and we're going to see why here in a bit. Source capture typically requires a smaller hood, smaller air volume, and air volume and static resistance. Those two numbers, the higher they go, the larger the capital expense the customer will have to make. The second area is ambient, and of course, you have natural circulation patterns in the facility, and a lot of times source capture can't handle that, and you have to be flexible. So now we can at least clean the area. We can prevent the weld fume from carrying from one area of the plant to another. For example, let's say we're welding in one area, we're doing paint work in another, and the weld fume, although it's a very fine dust particulate, submicron particulate, it can get into the paint and cause the painting to be a problem and rework to be done. So those are the two we're going to be talking about. And of course, at the very bottom there, you could possibly design for a combination of both source and ambient cleaning. So let's jump into source capture here. Source capture, we have to design a system. On a clean sheet of paper, a system consists of 4 components: the hood, the duct, the collector, and the blower. And you notice the order in which I read those out. We must design the hood first. A lot of times we'll get a call and they'll go, oh, I already have a dust collector. Can you make it work on this hood? Well, we still have to start with the hood. What is in the hood design? Then once we know the air volume of the hood, we can go to the duct. Then we can go to the collector, and then we can choose the blower. And we're going to step through that here in the next few slides. There's also variables involved. We're still dealing with the physics of air. CFM equals velocity times area. All of you have probably learned that formula backwards, forwards, inside out, upside down. In our world, that's all we do 100% of the time. The variables involved with industrial ventilation are not the same as HVAC. HVAC is still the physics of air, but the variables are different, and you're going to see how that comes to fruition here in a moment. The objectives, though, are to accurately predict the air volume and the energy required, and you see a picture there of the Industrial Ventilation Guide. This is a book from the American Conference of the Government of Industrial Hygiene. This is the Bible of our industry. This is where the information comes from. We, of course, have it in our own written form, but this is the Bible that everyone typically will fall back to in their design. The goal here is to end up with a system that meets the performance criteria of your customer. So let's start with the hood. As I said, it is first. The objective here is to minimize air volume required and to minimize energy required. So let's expand a little bit on that. Air volume, you could design a hood that requires 1,000 CFM. You could then say, well, if 1,000 is good, I'm going to use 1,500. Well, we want to minimize it to will work, but as we drive the air volume up, energy will go up as well. So going above and beyond is a good thing, but maybe not such a good thing. Common mistakes that we run into in the design of the hood, of course, is the wrong style of hood can be chosen. The location of the hood can be wrong, and the airflow could be improper. If the hood requires 1,000 and we deliver 500, we're going to have improper capture of the weld fume. Here are a few of the various hoods that can be used in a welding and, of course, in other types of dust collection. Each one of these hoods, though, carry with it a resistance and an efficiency rating. The raw edge hood is the least efficient of all the hoods. I'm not going to get into the detail and the engineering behind why one is more efficient than the other, but if you look at the bottom right, the bell mouth hood is classified as the most efficient hood. So I can design with this hood or the raw edge, but I must put into my calculations the static loss that is created by one hood design versus the other. So here we're looking at a canopy hood overhead, and you can see the middle video where a large amount of smoke is being emitted. To the right of that, you see a little less smoke. The video in the middle is showing an abundance of smoke, where a realistic welding would be more so on the right. If you'll notice, the hood is positioned directly above. You also notice that it has a canopy around that. So the air is now pulled in from the bottom, and it works upwards past the part up to the top, and then the smoke disappears. So here we have a properly designed hood with the right amount of air volume. As you see, none of that smoke is getting outside of our canopy hood. Another type is an extraction arm. Here in this photo, you see multiples. There's a total of 6, I believe, extraction arms. These have the ability to move and place this small bell mount hood that you see my mouse hovering over close enough within a foot or 2 of the welding area to source capture the weld fume. So now let's talk about variables. The face of the hood, whether it's a bell mount, whether it's a canopy hood, etc., must be designed with the proper capture velocity at the face of the hood. You see down below, weld fume velocity typically is 100 to 250 feet per minute. But we have to be careful in this design because a lot of times your welding process has an inert gas shielding. And if that gas is disturbed, as I mentioned earlier, porosity could set in. So having too much air movement, too much velocity could be a problem. But typically speaking, we're somewhere between 100 to 250 feet per minute capture velocity at the hood. As I mentioned, too much air can be a problem. It'll capture the gas. It will lead to an increase in cost. Too little air would mean I have fugitive dust floating around the plant. We have additional housekeeping that we have to deal with. Plus, I'm exposing my employees to the weld fume as it's being generated. So now a sidetrack here. Here was a project in a weld school for the military, and Donaldson was called in. This is a nonprofit weld school that was trying to realize a mission to help U.S. military veterans transition their careers from the military into the welding field. And of course, we visited their site. We looked at it, what they had. We tailored a fume capture system to provide a safe working environment for their future students. It all started with hood, as you see to the left photo there. You have the duct overhead in the middle. You have the collector, and of course a blower associated with that. We are happy to report that this unit is working fine. It captures 3 55-gallon drums of weld fume every 9 semesters. They in turn put that into recycling for further funding, and the chief academic officer of the military facility is delighted with the results, and we just wanted to share this is how it can work.
Thank you, Jim. I'm going to give you a chance to get a sip of water there. Just wanted to remind everyone, you can submit your questions as you think of them in the chat box. As I said, we will address all the questions at the end of the session.
Thank you for that, Ashley. I was on such a roll.
I know.
Okay. So now we graduate from the hood to the duct. And of course, another integral part. And if the hood and the ducting is not designed properly, the collector fails, and everybody points their finger at the collector when what caused the problem isn't necessarily the collector's fault. So we're going to look now at the duct design. And of course, the objective is very clear. We want to pull the correct amount of air volume from each hood. And we want to make sure that the velocities from each duct are running at the proper velocity, which we'll talk about in a minute. And of course, we will settle on a number, and we also can engineer above that number. But here we go again with energy consumption, and a lot of people don't want to spend more money unless they absolutely have to. Now, common mistakes in ductwork. Number one, the incorrect duct type, which we'll talk about. Secondly is incorrect duct sizing. That I see more than not in most applications. And then number three, getting an unbalanced design in a system, which we're going to talk about. Okay, so once again, let's revert back to the industrial ventilation guide that I mentioned. What are the proper variables? again, I've seen so many people walk in with an HVAC background, and of course, they understand the physics of air. They understand the flow rates, and they design, but the conveying velocities in an air conditioning duct that's moving air that has very little dirt and dust particulate in it is typically designed around 800 to 1,000 feet per minute. But as you see this chart here, the minimum for weld fume, according to the Industrial Ventilation Guide, is 2,000 to 2,500. But you notice that in our world, Donaldson Torrent, we take more of a common practice of 3,000 to 4,000 feet per minute. And of course, you're asking yourself, well, why would you do that? You talked about energy consumptions already. Well, what happens is when you design, let's say at 2,000 feet per minute, and then there's one variable in the dust collector, and it's monitored through differential pressure, and that's the clean air and the dirty air plenum. The only thing in between the clean and dirty air is our fabric filter barrier and the level of dust on it. As the level of dust increases, so does the differential pressure. As the differential increases, my air volume drops. So if I start at 2,000 feet per minute and I've got around a ½ inch to 1 inch differential pressure on the collector, as soon as I start to work and I go to 2, 3, 4 inches before doing a reverse pulse clean, my air volume will drop, and now I'm below 2,000 feet per minute, and that's what we want to prevent. So by designing in 3,000 to 4,000 feet per minute, we know we're going to capture the dust. We know we're going to convey it properly. If the DP does go up, it's going to still stay well above that 2,000 to 2,500 feet per minute. So insufficient duct velocities can cause safety issues as well. The dust collecting in the duct to the right, as you see here, this is not a weld fume application. A weld fume is a very light loading, which we will talk about here in a moment. But this is a dramatization of what you're seeing. If the conveying velocities drop below 2,000, you will see dust build up in this ductwork, okay? The NFPA guidelines, if you're dealing with a combustible dust, says no more than 1/32 of layer of dust in the duct, on the duct, in the rafters. So we've got to make sure our transport velocities are designed correctly. Okay, so let's look at a few things here. You get to chime in. You have buttons, good idea, bad idea. I'm going to show you something. Ashley's going to tell us the results. So here comes the first one. Everybody ready? So rectangular duct for the dirty air side of an industrial ventilation system. Is this a good idea or a bad idea?
All right, and just a reminder, the little face is where you get it, but we got a lot of thumbs downs coming through here. Oh yeah, everybody's got, I think it's consent. Nobody's okay with it. It's a bad idea.
All right, so nobody's cheating. They're not looking over somebody else's shoulder. Oh, wait a minute, this is virtual. So yes, thumbs down on that. Rectangular duct on the dirty air side. So again, typically when I see a rectangular duct put in industrial ventilation system on the dirty air side, it's someone with HVAC background. Why is that not recommended? Well, I mentioned briefly about having more than 1/32 of an inch of dust in the ductwork. Okay, if I have a rectangular duct, the velocities in each of the corners are going to be lower than my conveying velocity. Therefore, the dust will settle until my ID becomes round. So you're telling me I'm going to fill each one of those corners, primarily on the bottom, not necessarily on the top, but we're going to fill and we're going to capture the dust there. So that's why we say no to the rectangular duct. Okay, here comes the next one. Class 3 ductwork. Good idea or a bad idea for industrial ventilation on weld fume?
All right. Got some thumbs up, a couple thumbs down. They're coming in. A lot of thumbs up. I think we only have a couple that are thumbs down.
Okay. All right. Very good. Very good. All right. So when you're specifying for industrial duct systems, we want to make sure that you call out a heavy-duty industrial ductwork. Most dust collection applications use a class 2, 3, or 4 ductwork, which is designed to the SMACNA standards, okay? Typically, the higher the class rating of the ductwork, the heavier the gauge. So class 3 ductwork is considered a good idea for industrial ventilation. Okay, ready for the next one? Spiral duct. Good or bad?
All right. Thumbs down. We got a lot of thumbs down. Couple thumbs up though, but a lot of thumbs down.
Very good, very good. Okay, so spiral ducting is commonly used, okay? It tends, though, to leak air and could impact the design airflow by as much as 10%. So for most dust collection applications, I would say spiral is a bad idea, but for welding, it's such a light loading, we actually use quite a bit of the spiral ducting. Now, the disadvantage with the spiral ducting is if you have a facility and they're constantly rearranging, adding processes, moving equipment, and moving the ductwork, this stuff is dip-tipped and taped and caulked, and when you take it down, it can be destroyed and can't be reused versus clamp-together style ductwork that is out there that can be a cotter pin removed, a clamp removed, it can be inventory reused, expanded, etc. So, good, yes, bad, yes. This one can go either way. But for weld fume, we see it used, but we still would look towards the heavier duty. All right, here comes the next one. Flexible ductwork, good idea or bad idea?
All right. We got a lot of thumbs downs coming through here. I don't think anybody's got a thumbs up yet. It's all down.
Okay.
Oh,
so,
just kidding. We got a couple ups.
Okay. All right. Good to know. Good to know. So, flexible ductwork, a lot of downs, a few ups, and you see that in this picture you have a piece of flexible duct. Flexible duct has about 2 to 3 times the static loss that a galvanized piece of duct would be. So if you said thumbs down for that reason, you are correct. But you run into situations where, if you remember those articulating arms I showed, it has elbows that are covered in flexible duct, allowing you to move the hood around. Or you could have a hood, a hard automation hood, that is on a piece of equipment and that we may need vibration isolation. And so there may be a reason that we have to use flexible ductwork. So if we remember 2 things about flexible ductwork. Number 1, you see this picture and you see the orientation. It looks like a snake. If I use flexible ductwork, my goal is to keep it as straight as possible and as short as possible, okay? I've walked into plants before and seen a 100-foot run of 4-inch flexible ductwork, and it looks like an accordion, up and down, and they wonder why they have no air volume at their hood. It's a 4-inch duct, yes, but it's not straight and it's not smooth. They didn't allow for the static loss. So in your calculations, you may have to use flex duct, therefore allow for it, and it becomes a moot point. So very good on everyone's part there. All right, here's the last one. Are you ready? Buttons ready? Go. Branch entries with a T or a hard 90 degrees. Good idea or bad idea?
All right, we got thumbs down coming in. Lots of thumbs down. Across the board here, thumbs down.
Thumbs down. Okay, well then I don't even need to talk about the next slide, but I'm going to do it anyway. All right. What you see here, of course, is elbows, what is considered preferred in industrial ventilation. Again, A lot of times you may work in HVAC capacity, but when you get a dust collection project, it comes with different variables. The preferred elbow is 2 to 2.5 centerline radius elbows. Acceptable is considered 1.5. We want to avoid hard 90s or 1.0 centerline radius elbow, which is what you see in HVAC. Then we get into branch fittings, and you see that the preferred is coming in at a 30. It says not recommended, but this is used a bit, 45 degree, but we see the word avoid. We never want to see a 90-degree T in an industrial ventilation. Why? Because remember what our conveying velocities were? Our common practice for weld fume is 3,000 to 4,000. You get into other dust from shot blast, plasma cutting, pharmaceutical, grain, whatever it may be, we're hauling a lot of dirt, dust, particulate. That intersection right here, this air coming here, we're coming at 4,000, 4,500 feet per minute coming in through here. And to stop and turn this 90 degrees, imagine the static resistance created with this design that we say avoid versus this design, okay? So hopefully that clears up a few of your questions. All right, we mentioned about having a balanced system. So here lies a layout, and you can see here that we have two existing workstations, one with a backdraft hood, one with a canopy hood, and you see the ductwork was designed. We see the intersection. This is coming in. This actually looks like a 45, might be a 30, but then we graduate to a larger, so we maintain our transport velocities all the way back to the collector, okay? I don't know how many times I have seen this, but a system is designed. You engineered it, it's engineered correctly, and they install it correctly, and it's a beautiful thing. And then the operator, the company says, hey, we need to add a new process. Put it right here, tie it into this ductwork. OMG, what did we just do? You just changed the entire engineered design of this system. So now I've got this air volume, we'll just call this 1,000, this 1,000. I've got an intersection of 2,000, and I introduce another 1,000. Well, I need 3,000, I only have 2,000. So what's that going to do to these two locations over here? These two are going to have inadequate airflow, poor capture, conveying velocities will be reduced, and you can see we're going to start having complications. So here's my number one recommendation to each of you. If and when you design an industrial ventilation system and you deliver that design to the end user, if they want to change it, if they know they need to change it at some point in time, one, you can design future into it. Two, you can say, call us before you do it. And then you get with us, we can work together on making sure that whatever we do, it's done so that the system does remain as balanced. Okay, so now we're shifting away from hood and duct, and we step into the dust collector. Okay, the objective here is to deliver sufficient efficiencies with an operation that is predictable, stable, and has an economic fashion here. The common mistakes we run into: one, I chose the wrong filtration technology. Okay, Donaldson leads in technology. There are cartridges made of many varieties. We make them all, good, better, best. Okay. You can choose the wrong size of the collector. We're going to talk about that. And then, or you can choose the right filter technology and the right size collector, but you can install it wrong. So just because you designed it right, you have to make sure that your installer, mechanical contractors, are putting it in correctly so that we do get the maximized performance. All right. So we're talking weld fume design here, and we pop up with a cartridge collector. And I want to preface one thing. Donaldson Company, we manufacture with the widest and deepest product line. We make cartridge collectors. We make bag houses. we make cyclones, we make mist collectors. So when you come to us and you say, I have weld fume, our number one recommendation for this application is a cartridge collector. And we're going to explain the reasons why. If you come to us with a different type of application, say woodworking, heavy loading, fibrous, spherical dust, all combination, all of the above, we would then look at some type of bottom entry with a vertically hung filter to do that job. So the good thing to know about Donaldson is we make both. And when we recommend one versus the other, it's because it's best for that application. What I see a lot of times in our opposition is they make one or the other, and they're going to steer you down that path. Why? Because that's what they build. In our case, if we say you need a cartridge collector and you tell us, no, I want a bag house in this design, fine, we can do that too. So I wanted to preface that before I got into why the cartridge collector is best suited for weld fume. Number one, it's going to be a smaller footprint than a bag house. Thus, the cost is going to be lower. The application for weld fume is typically 2 grains per dry center cubic foot or less. Okay, so we have a very low dust loading on the application. Plus, this is a very fine submicron particulate. It's usually uniform, spherical in shape, and it's, again, ideal for cartridge technology. The cartridge collector that you see has continuous duty capabilities. So if you're in a high-level production, you can run this 24/7, and it will maintain the proper differential pressure, the proper air volume online 24/7. We use the compressed air in the plant to reverse pulse. And then, of course, the cartridge filter media we will talk about momentarily. But before we do that, let's look at the evolution of a cartridge collector. A lot of people don't realize Donaldson Company, as Ashley mentioned earlier, we've been around over 100 years. Back in 1970, we put the first cartridge in a bag house. This is a vertically hung cartridge. The air comes in the bottom and it turns up. Okay? A cartridge versus bag. It's a pleated media. It has more square foot of media in the same footprint, and therefore we can do more, but we still have to calculate with the right air to media ratio. Okay? So the air comes in low, it turns up. We also have to calculate a certain can velocity with this design, because as we reverse pulse, we want the dust to fall. The airstream on light dust is going to want to try to re-entrain. So therefore, this continuous duty collector just became intermittent duty because I need to shut it off and do a downtime clean. So we then graduated in the later 70s to a side entry going, okay, we can take a lot of this dust in through the side, but it's still, we had a third-party fluid analysis done, and the air volume still goes down to the bottom and up through the filter. So can velocity, again, is a variable that must be included in your design. Then in 1980, we introduced the first horizontal filter. The air comes in high and it works down. In the industrial ventilation guide, which is the Bible of the industry, they had a third-party EPA-sponsored test that says the downward flow of air is less likely to have redeposition of dust on the cartridge. So for a light loading weld fume application, this is a premium choice. And of course, you can see now I can get a little more aggressive with my air to media ratio just by the orientation of the cartridge. Then finally, we introduced in 2014 the DFE, and it has still a high inlet downflow, but the air comes in right on top of a metal venturi in the dirty air plenum. So if your dust is abrasive, it's going to take the brunt of that before turning to the filter and doing what it does. Once again, notice the air to media ratio. So now I can do the same job with this collector with less filters than I could do with this collector here. But the good thing is everything that I've talked about, Donaldson was the first one to create this, to pioneer this. Opposition has copied and followed every step of the way. So we're glad to say that we have had our hand in this, and it is still part of our design unless we elected to rationalize. Okay, So let's look a little closer at the downflow evolution, and we won't spend a great deal of time, but the DFE, as you can see from this photo, it has a very small footprint. We have taken the advice of people over the years, and we've incorporated a lot of things in this. Number one, the filter is triangular in shape. Some people will say build up on top of the filter. Well, we've minimized this from a 25% to a 13%. The filters have keyways cut in them right here, as you can see, where the filter, there's a asymmetrical yoke that prevents you from putting the filter in backwards. Oh my gosh. The face you see here has a metal cap. You can see the gasket seal here. Well, there's another gasket on the other end. The gasket's going to the tube sheet. So it's imperative that you put the filters in the right way. These can be removed without tools, or you can use the hex nut ODID to take these out. They're hinged, they open, and most importantly, the operator is working in a non-confined space. And one individual can take a filter out with dirt on it weighing less than 50 pounds by himself or herself. So just giving you that high level, and of course we can give you much more detail if you need, let us know. We also make, we've talked about centralized large systems. We also make roll around. And this, of course, has a source capture, articulating arm, plugs into 110. It's adjustable, lightweight, and it can be used. Now, I'm going to show you this unit in operation. There is Weld.com out there that makes welding videos, and they recently made one using our Easy Truck. So I'm going to go to that now and play a clip so you can see how it works. Note the proximity of the hood in relation to the work so that the thermal rise of the fume goes into the hood and not into the operator's breathing zone. So here we go. Until we get it right. Until we get it right. Until we get it right. Pretty good stuff. So that shows, like I said, the smoke going into the hood, accelerating and disappearing. Now, when we look at the filtration technology that I mentioned in the very beginning of this segment, filtration technology, again, is something that Donaldson has pioneered over the years. We make, again, you see in this slide here, we make a cellulose type filter. This is going to be the lowest cost filter that you can buy. And a lot of people, they say, I'm looking for a lower price. Here we have what is called ultra-web nanofiber. And this is worth talking about. Most of you, and probably all of you, have by now heard of nanofiber. Nanofiber, Donaldson has created and had in production and in the working world for over 40 years, 4 decades. Some people are just now getting to the point where they can do that. What does this nanofiber mean? Okay, take a look at the cellulose filter, which, by the way, we make. You notice this red dot. This red dot symbolizes a dust particulate that is 10 micron in size. A hair on the top of your head is 50 micron. Okay, so this is 10 micron, and weld fume is submicron particulate. So this 10 micron in our world is a boulder. So submicron, where is the air going to go? It's going to find its way through this cellulose filtration media, and it's going to find these avenues, and it's going to go deep. And then it's going to lodge in against the cellulose, and then we're going to reverse pulse it, and it's going to hopefully pulse off. But when this dust gets so deep on us, our differential pressure goes up. It remains up because when we pulse, it doesn't clean as efficient as a nanofiber. Look at the nanofiber. This cellulose filter has a cellulose base with the nanofiber webbing. This 10 micron is stopped on the surface. So when I reverse pulse, it is released much easier. So I operate at a lower differential. I'm able to pulse down easier than I would on a cellulose. The other thing, most critical, is the cellulose filter will not last as long. I had an application. It was on the Corian surface prep on a wide belt sander. They put in a cellulose filter after running 12 months on our UltraWeb nanofiber. They bought a cellulose filter for half the price, and they ended up changing that in 1 month. They got 12 months life out of the UltraWeb nanofiber, 1 month out of the cellulose filter. Do the math on that. You're buying the filters 12 times versus once, and you're putting labor to change them out 12 times versus once. Which one actually does cost less? So another thing to look at, with the UltraWeb FR, that is a flame retardant material that we would be using in welding, it is rated as a MERV 15 filter. That is our primary filter on the dust collector. A lot of times in weld fume, they'll recirculate the air back into the facility. So you would want to add a safety filter or a HEPA filter. That's a 99.97% efficient. That's a MERV 16, MERV 17. So what we're saying is the UltraWeb nanofiber FR is almost equal to a HEPA filter. The HEPA filter is a static filter. When it loads, you have to throw it out, and they're expensive. The UltraWeb nanofiber is not as expensive as a HEPA filter, plus I can reverse pulse it, and it's going to last so much longer. So when you do decide to recirculate the air back in the plant, putting that safety filter is there in the event you have a breach on the primary filter. So I'm going to show you that here in the next slide, which is an actual installation in Oklahoma that I was involved with. And you look at the photo to the left, and you can see the articulating arm. You can see the laterals coming into the ductwork like we talked about. There's the return air coming in. You can't see the HEPA filters on that, but we are recirculating that with a safety filter. These arms articulate. Behind the wall is where they're doing their coupon work, whether it be pipe, plate, etc., flat, horizontal, overhead. And then you have the arm, you can swing it out for freelance welding. Let's say the school wants to build a smoker and raffle that at the homecoming game. And so now the welding school is going to do that for them. Shift your attention now to the outside, and we've got the first thing you see is a spark cooler. This is a spark arrestor. If an amber gets into the system and the amber is lit long enough and gets to the cellulose / nanofiber, FR means it will burn as long as it has a match to it. But if the amber extinguishes itself, it will quit burning. But we still have to take precautions, and this is a passive device that takes the amber through a tortuous path, breaking it open. As it's broken open, that inner core where the heat is exposed to oxygen, and it will extinguish. So then the air goes through the collector, down through the clean air plenum to the blower, and in this case, we return the air back in, or we have the option to exhaust the air out the stack. This is a summer-winter diverter valve. In this case, the school would heat in the winter, and they would heat that, and you don't want to throw the heated air out, have to make it up, so we recirculate that back in. In the summer, they don't have air conditioning, so they pull the clean air through the open doors and send the filtered clean air out, straight out of the collector.
Thank you, Jim. I'm going to let you get a sip of water here. We do have just about 10 minutes left of the webinar. Just so everyone's aware, we will answer all the questions. I will make sure I email all of you if we do not get to all your questions at the end here, but hang tight. We will get to it.
Thank you, Ashley, again. Okay, fan design. Again, this is the fourth component of industrial ventilation design. Hood, duct collector, and now blower. Okay, objectives, volumetric flow at the required fan static pressure. Okay, so many people miss that mark. Okay, And we also want to maintain the energy efficiency, so we don't want too much, but we can't have too little. And we want to make sure the noise level. Common mistakes. 1, the poor fan selection. Number 2, the right selection can be made, but it can be installed wrong. And we're going to address that. So here's a typical exercise where I need 9,000 CFM at 12 inches of static. Well, Jim, where are you coming up with 12 inches? Okay, let's address what we just did. So this is a little review. The hood typical requires about 1.5 inches of water column. The ductwork, in this case, we're a little slower velocities, 2.5, but this number can get bigger as well. Then for the dust collector, the filter section, 6 inches of water gauge. And you're going 6 inches. Every time I look at a collector, it's got maybe a ½ inch or 1 when I start it up, and it operates around 2 or 3. Why are you putting so much? That is an upset condition. Let's say that third shift comes in, they elect to turn the compressed air off, or the compressor goes down. Now we're putting all of that weld fume into the collector. It says it's reverse pulsing, but there's no compressed air. We're not knocking down the DP. So I still have to keep my air volume at the hoods, so I have to allow for that upset condition. Then we have the filter to fan loss. That's a compression point. So that's another 1 inch. And then that spark arrestor, spark cooler that I showed you earlier, that has a loss associated. And most people, they go into an existing system. Oh, I need to get compliant. I need a spark arrestor system. Okay, they put it in. Their blower was not sized properly to begin with. Now it fails. Whose fault is that? The dust collector? No. So these are the things that you have to look at in your design. So now let's look at, we said we need 9,000 CFM at 12 inches. So there's 12 inches on this curve. You notice those are 8 different fan curves, and we're trying to choose the right one for this project. So 12 inches is our engineered design point, 9,000 CFM. Draw the lines. The intersection point is not falling on the line. So now we have to choose. Do I choose a TBI 25 or a TBI 30? The answer is a TBI 30. What that has just done, we've moved the 9,000 up to this intersection, and it now says I have 13 inches of static versus 9.5 inches of static if I happen to choose the TBI 25. So you can see I could have chosen the wrong one, but I had 9,000, but I didn't have my static. Okay? All right. Then we talked about installation. This one kind of really takes it all. That's one of our beautiful collectors, but then the ductwork was installed. The mechanical contractor puts a 90-degree elbow right into the inlet of the duct. There are no turning vanes. The air is going to run the outer wall of this elbow, and it's going to lopside our fan, and we're going to have a system effect loss in our fan because it's not designed right. I should have a minimum of 3, but preferred 5 diameters of straight run of duct going into this blower. If I can't get that in the spacing, there are inlet boxes that have turning vanes in them that will allow you to load that fan wheel properly. And then on top of that, they put a rain cap on top. The rain cap will prevent rain from getting in, but there are drain holes that can the plug remove and left open and allow, if rain or snow gets in, it will work its way out. But this is causing a back pressure. So once again, I needed 9,000 at 12 inches of static, and you're adding this resistance, and my resistance demand is now greater than 12. I hope it doesn't exceed 13 because that's all my blower will have. Okay. Ambient collection, we'll spend a little bit of time because, as I said early, source capture, 95% of installations I've worked on have all been source capture. But a source capture isn't always the best way based on a few things. Of course, with ambient, we are taking the air as it floats up into the rafters, and we're going to circulate that air. This enables us to be flexible in our floor design. When you have a challenging floor layout, we can deal with that. And of course, you can supplement source capture and ambient as a combo to do a job effectively. The challenges are, of course, you're constantly manipulating the workstations. You have natural ventilation, whether it be windows, doors, forklifts driving by, change in level of productivity. So all of these variables have an effect. But we have a couple of units that fit into this ambient. One is the newly founded downflow ambient, DFA, and it, of course, is a tower that stands tall, and it takes up a very small footprint. The other one to the right is the AT3000. This one, as you can see, it's got all threads here. It's actually hung in the rafters, and depending on the area, we create a racetrack. So as the weld fume gets to that area, it gets into a push and a pull to where we evacuate and change that air out. So how do we go about designing this? We have what is called a facility modeling tool that takes a look at the airflows. And as you see in this, we're looking at this area. There's 2 blue towers, DFA towers, and 6 welding stations to do this job properly. Well, what does this look like? This is the type of printout that we can get for a local mean age of the air as well as the velocity field. Like I say, in the velocity field over here, we're dealing with this design at 400 feet per minute or less. And that is adequate variable for welding when using an inert gas shielding. If I had velocities greater than that, I'm going to see disruption by putting in some type of ambient clean system. So just like in source capture, there are variables involved, and you have to know which ones are the right ones to pick. So I touched on them. You have the potential for airflow disruption, and in this case, you have a low, moderate, and high. Fume generation, the different welding processes, TIG welding is very low. You get into flux core gas shielded or flux core self-shielded, that's going to be very heavy. So each one of those require a certain air exchange rate per hour. The low, for example, is showing 4. Okay, that means I'm going to change the air out every 15 minutes. If I go with high and I say I need to change it 15 times per hour, I'm changing the air out every 4 minutes. So choosing the right variable, then it's kind of like the hood duct collector blower, choosing the right hood, then I can design the rest. Choosing the right air exchange rate, then I can design the rest. So here's a typical exercise. I've got a 100-foot by 50-foot facility with 20-foot ceilings. My target air exchange rate is 8 air changes. So 100,000 cubic foot divided by 8 air changes says I need 12,500 CFM. That would be 2 towers or 4 of the AT3000s to accomplish that. Okay, I know I've blown through a great deal of information. I hope that it's been informative for each and every one of you. I do hope that you can take this information and then go forward in helping design and sell the industrial ventilation systems. But I do want to encourage you, when you tackle the next project, if you have questions, concerns, I work directly for the Donaldson company. I live in Oklahoma, covering Oklahoma, Arkansas, a small part of Missouri. There's 30 other guys, girls like me in the field that do the same thing. We do nothing but design and sell industrial ventilation systems. So we hope that you would reach out to us if you get into a situation and you would like support on your design. Thank you so much for your time.